Good afternoon, everyone. I think we have same time now, isn't it? Melbourne and Rockhampton have same time from this week, so maybe some confusion. Some of you might, those who are in Melbourne, might join 1 hour later. Okay, because you used to join at 3 o'clock. But from this week it's same time. Yeah. Okay, so let's see. Anyway, we'll start, and those who missed late should be able to catch up using the recordings. So the beam design tutorial 2 has been completed, and from this week, as I told you, we will use both classes to discuss the tutorials. So last week we started about the serviceability condition. Okay, we'll spend a little bit more time with the beams, because if you understand the beam design, the slab designs are quite straightforward. Okay, it won't take much time. So we have So the ultimate limit state we discussed with the tutorial 2. We'll talk about serviceability. Actually, we talk about the serviceability in tutorial 1, but some of you asked to review that one again, so we will look at that one. So in the serviceability limit state, as I discussed last week, it's about the service loads, which is much less compared to the ultimate case. Okay, so when you have a smaller load compared to ultimate limit states, they found the deflections are smaller, so the behavior of the concrete beams can be considered as elastic. Okay, as elastic. So that means the entire stress and strain values are within the elastic range, so we don't reach the yielding point or flow stress. Okay, so that is the consideration we used in the serviceability limit states. Okay, so the tutorial 2 ultimate limit states considered completely different conditions. Okay, so here this elastic range. So if the material or cross section is within the elastic range, according to the strength of material theory, the neutral axis will pass through the centroid of the section. Okay, the neutral axis is passed through the centroid of the section. So here they use two different cases. Okay, one is uncracked section. So the section is not cracked. Okay, it's not cracked. So we have steel, so when you have two different material, everything elastic. Okay, it's elastic, fully elastic. So if you have two materials, finding centroid is problem. why I need the centroid? Why I need the centroid? Because if it is elastic range, if the material is within the elastic range, the strength of material theory says the neutral axis will pass through the centroid. Okay. So this is true for elastic material. If it is past the elastic range, it is not correct. Okay. So if you have a cross section, say for example, centroid, so neutral axis will pass through the centroid. Neutral axis will pass through the centroid. It can be any axis. Neutral axis can be this way or this way. Okay, depend on how you apply the bending moment. Okay, but always neutral axis will pass through the centroid. Okay, so that is what we had. That is what we have in the strength of material subject. So here, to find out the neutral axis, I am going to find the center of gravity or centroid. Okay. If you want to find out centroid of a section which is not uniform, we use some theories. Yeah, this is the centroidal things. Yeah, so we need to do this one because it is not a rectangle, it has something else. Okay, so if I want to use this one, the whole cross section should be made of same material. But here this is concrete, this is steel. Okay, if I want to use this one, the cross section should be made of same material. It is not same material, two different materials. So I need to transfer this one into one single material. We have concrete and steel. We have concrete and we have steel. Yeah? So I need to transfer the entire cross section either as a concrete or steel. Okay, so I'm going to transfer the whole section as concrete material. Okay, so I'm going to replace the steel with concrete. So if we want to replace the steel with the concrete, the steel is strong. If you look at the E value, okay, not talking about the capacity, this is the elastic modulus, elasticity. So elastic modulus, this one is higher. This is 200 gigapascal steel. Concrete around 30, 32, something like that. So if you replace the steel with concrete for equivalent stresses, you need more concrete. Okay, because you can think it is not the stress wise, but you can think steel is stronger. So if you want to replace with concrete, you need more. Okay, So if I want to replace steel with concrete, I know more concrete is required. So what is, how much more? So again, center material theory side, you need this much of time concrete. Okay, so the equivalent area for AST is equal to in times okay to replace by concrete, we need this much of in times AST. In times, so n is equal to this one, yeah? Both are equal. So roughly this is around 6 point something, because this one is 200, concrete one we don't know, it is depend on the grade of concrete. Yeah, you should be able to get it from the section 3.1. so it is 32 gigapascal. Okay, so this is 6.102 ratio around. Okay, 6.2 or 6.5, maybe almost 7, no? Maybe around roughly. Okay, it is not correct number, because you need to know the E value of concrete. It is depend on the grade of concrete. If it is 32 MPa, E value is 30.8. If it is 40, it will increase. Okay, so say I can say around 7 times of area. If this one is 100 millimeter square, the total steel area is 100. I need around 680 square millimeter concrete. Okay, 680 roughly concrete. So if I replace this area with, say for example, (32 MPa), EC is equal to, I think, 30.8 gigapascal. I think it is given in the 3.1. If anyone check quick, I will check that one so that so 30.1. So you can see this is the table. So for 32 it is 30.1. For 40, 32. It will go up to 42, 45, something like that. Okay. So the EC value is different. So this is 30.1. This is 30.1. So if you put the N value, 200 upon 30.1. So if you calculate, (200) divided by 30.1, 6.64, this much. So that means if area of steel, so let's say 220 millimeter square, okay, so then we need 6.64 times of 220 of concrete to replace that one. Okay, is that clear? So if it is 220 multiplied by 6.1, you will have 146.2. So you need this much of concrete. So to replace 220 millimeter square steel, we need 1462, okay, square millimeter of concrete of 32 grade. So I'm going to remove this one, okay. To explain, I use these numbers to explain. Use these numbers, okay. So as I told, this is 220. So I'm going to replace. The, it's not correct, so the whole concrete will stay there, and there are 3 holes, yeah. So I'm going to replace, so I'm going to remove the steel bars, yeah, and want to put it everything with the concrete, yeah. So first we need to remove the steel bars, so there will be 3 holes, okay, the bars areas. So I have around 6.64 times of the area. First I need to fill the holes, okay. I need to fill the holes, so that means 220 gone to fill, yeah, 220 gone, so 220 to fill the holes. The remaining 42, so I need to put the remainings at the sides. So I need 1462, but 1220 has been used to fill that holes because I need to remove the steel bars. So the remaining need to be placed here. So is everything now is fully filled. So the remaining will go on the same level and put in both sides. So half here, half here. So 600. It will be 621 on each side. Okay, so my cross section looks like this. So how much this area? This one plus the whole things is n times of the AST. Okay, if it is AST is here the n times of AST should be placed. Okay, but one AST goes here to fill the holes, so remaining part EST times n minus 1 or n minus 1 EST. Okay, why this minus 1 comes? Because that one part of EST used to fill here. Okay, so this area plus this area plus this area is equal to n minus 1 times EST. So I need to find out the centroid of this whole area. So now it looks like this one. Huh? So if you look at that outline, yeah, this one looks like this. So I need to find out the centroid. So what I will do is I will divide this one into two known areas. So this is one rectangle and the remaining areas. So I put something like that: section, area, yi, ai, yi. Okay, we will do this one. Rectangular section, B times D, that is the area of the rectangle. B is the width, D is the overall depth. The replaced concrete, the area is n minus 1 EST. N minus 1 EST. Okay. So where is the yi? Yi is the centroid distance for each sections. So I am going to measure from the top. Okay. I am going to measure from the top. That is here. So this is small d, this is b, this is the d. So you have all the drawings or dimensions shown in the tutorials one. Okay. So for the rectangle, it is somewhere in the middle. Yeah. For the rectangle, it is somewhere in the middle. So from the top, it is capital D by 2. Yeah, I'm measuring everything from the top. Is that okay? D by 2. For the replaced things, from the top for this area is a D. Yeah, it is D. So AIYI B D squared by 2 n minus 1 D AST. So I will add this one, B D squared by 2 plus n minus 1 D times AST. I will also add this one, BD plus n minus 1 AST. So y bar is equal to, I don't know where is the centroid, but centroid will be somewhere here. So this is what I put as a y bar. Uncracked section, I put UC, uncracked UC. Okay, so that is basically y bar, that is equal to y bar UC in my tutorial or study guide. That is equal to sigma AIYI divided by sigma A. So if you put this one, BD squared by 2 plus n minus 1 D AST Vd plus n minus 1 est. So this is what I gave, or this is what it is given the solutions. Okay. So you should be able to solve this one, or that equation. They take the moment about the neutral axis, that's also fine. So whatever the way you want, you should be able to get it. Okay, so you don't need to. So in the solution I gave the yi, the solution or study guide, I used to measure the yi from the neutral axis. So I measured everything from here rather than here. Okay, so the distance, this is d by 2. So when I measure the distance from here, it is d by 2. When you measure the distance from here, it is yuc minus d by 2. This distance you need to provide. Okay, so the yi is different, but if you solve, if you put the values here or in that equation, both will give the same answer. Okay, so that's what I always said, you don't need to memorize anything. So the tutorial solutions, don't say that it is different from what you learned just now. Here they said about the neutral axis, I take the moment about the top fiber. Okay, so both will give the final answer same, but the path might be looks slightly different. Okay, so I know the neutral axis for the whole section. So that is the neutral axis. Why I need the neutral axis? So technically I found the centroid, and for the elastic materials, the neutral axis will pass through the centroid. Okay, why I need this neutral axis or centroid? What is the purpose? When you do something, you should know why we are doing this one. Because to find out deflection, I need I value. Okay, so the deflections equations, or deflection of any member. Okay, the deflection. So if you have what is the maximum deflection? So this is 5 upon 384 WL to the power 4 EI. E is the E value, E is the elastic modulus. I value is important. Stiffness. Yeah. So to find out deflection, if it is a point load, everywhere, when you have the equation for deflection, you will see it is function of I, the loading, length, load, length, E, I, 4 important parameters to find out deflection. Load you already have, length you know, okay, E value you should be able to find, but the problem is I, second moment of error. To find out I, to find out I, you need the neutral axis, because I is about neutral axis. So those who forgot the neutral axis things, I value BD cubed upon 12. I value dB cubed upon 12. So about the centroidal axis, the I value for rectangular section is BD cubed upon 12. So B generally parallel to the axis, D is perpendicular to the axis. You can see the cube comes to the D, which is perpendicular to the axis. So here this is the axis, perpendicular that one is B, so that's what is dB cubed. Okay, so this is the second moment of area of a rectangular section. So to find out deflection, I need I value. But here the problem is, it is not simply a rectangle, it is something like a different shape. Yeah, it is not rectangle. If it is a rectangle, it is easy. So I need to find out the I value about the neutral axis. So for this rectangle, it is the center. So now we have a new neutral axis. It is slightly below. And we also have an area here. Yeah. So I need to find out the second moment of area about this axis I, uncracked section. Okay, or otherwise I effective section. So how to find out about this axis? It is two different areas. It's quite difficult. So I will divide into 2 plus the equivalent steel area. Okay. So I divide the whole section into rectangle and this shape. Okay. So how to do that? So we'll use the parallel axis theorem in the second moment of area. The parallel axis theorem says if you have an area, it can be any area, you have a centroid, so you have a I value about centroidal axis. Then if you want to have the I value about another axis which is parallel to that, so this is equal to the centroidal axis I plus E d square. D is the distance between these. So the I of any axis can be given as Ig plus AD square. Okay, so these are basically whatever we discussed. It's in the strength of material. It is not concrete design. Okay, it is not concrete design, but I am repeating this once because I think that's caused the problem. If you don't understand what's happening, you don't have any idea what I am writing. So all these ones comes under strength of material. Normally they don't explain these things in the concrete design textbooks, but they will use this. Okay, so I'm going to use this one here. So I rectangle, this one. Forgot about this, the extension. Look at this one. So I need to find out about this axis, but for the rectangle, this is the centroidal axis. For the rectangle, okay, don't look at this one. For the rectangle, about the centroidal axis, this is the centroidal axis, this is the center. That is equal to BD cube upon 12. About this axis, centroidal axis, BD cube upon 12. So BD cube upon 12, that is the Ig, plus area times distance square. Area, what is area? BD, yeah, the distance between this one and this one. I am finding the I value about this axis. This is the centroidal axis, the distance. So this is d by 2, this is y bar. So the distance is equal to y bar minus this. So this is the I value for the rectangle section about the red line. What is the red line? That is the neutral axis which passes through the centroid of the whole section. Then I need to find out I equivalent steel area for this one. Forgot about this rectangle, the blue color ones. So that is just an area. This is n minus 1 AST. So that is the area. The blue color one, area. So if you have an area, second moment of area is equal to area times distance square. Area times distance square. Because this doesn't have any dimensions, okay? That doesn't have any dimensions. Only the area is given, okay? That doesn't have any dimension, it's only the area is given. So if you have an area, the second moment of area is equal to area times distance square, okay? Where the thickness is very small. Generally it is very small. It's only the diameter of the bar. Compared to the overall dimension, the size is very small. So area because I is equal to area times distance square. So the area distance from here to here. From here to there, small d. From here to there, small d. Yeah? This is where we put the steel. Steel is at small d distance. Small d, this one is y bar. So the distance is small d minus y bar square. So this is area and this is distance. Okay, so if you add, you will get I value that is given in the here. This is the area of the rectangular section, this is the area of the equivalent steel. Yeah. So if you substitute, you have all the values, you should be able to find out. So this is the second moment of area. This is the second moment of area of uncracked section. Okay. So the second moment of area calculation, technically, it's not concrete design. Okay. It is not concrete design. Is it clear? So this is for uncracked section. Then we look at the cracked section. So cracked section means, so you have the steel, so you have the section. Now some of the concrete has cracked. So if concrete cracked means it cannot take any loads. Okay, concrete cracked means it cannot take any loads. So I am going to assume this is the compression part. This is the compression part. All the tension part has cracked. Okay, all the tension part is cracked. So this is concrete, and so all the concretes here has cracked. But we have steel. We have steel. Okay, clear? So here this is neutral axis. So this is B. So this is cracked section, Y bar cracked. Okay. I need to find out the Y bar using same way as earlier. But I had two different materials, so I am going to replace everything with the concrete. So concrete remain as it is. So the steel section need to be replaced with the concrete. The steel, so which one we need? This much of steel. Okay, so N times AST. Here I don't put N minus 1 because we don't need to fill, everything is empty because there is no concrete below that line. So you can put N times AST. So earlier one part of the AST went to fill the holes in the bottom concrete area. But here we don't have any concrete, only the equivalent steel, equivalent area for the steel will be there. So this is the equivalent area. So this is the crack section. So this is the equivalent area made of concrete. So you can do the same work. So this is the neutral axis. So I need the eye cracked. I need the eye cracked. So I need to find out the depth of the neutral axis. I need the depth of the neutral axis. So we have two, section 1, 2. Yeah, you should be able to follow the same things. Please try. The answer is given. Okay, use the parallaxis theorem. For you need to add this I value plus this I value. Okay, so this is B. So please try. If you still have problem, ask me. It is exactly same work as we discussed now. Okay. So if you want to find out the deflection, the one thing you need to know is the I value for cracked and uncracked section. So that's what we discussed now, how to get that. Then you need to go to the standards. So if it is a simply supported, the deflection is 5/32, so this one. So if it is a simply supported, for different loading condition is different, but I think the tutorial I used the simply supported. So the equation is this one, deflection. So the load length EI, I already calculated, but if you look at the relevant standard, they said how to use the equivalent I value. Okay, let's show that one. If you have any problem, just ask me. So this is the standards. So they said how to find out the deflection for short term and long term. Okay, for short term they said for simply supported, find out the deflection at the midspan, that is given by 5/384 WL to the 4 EI. That equation normally again will be given in the statics books or strength of material books or any textbook. Analysis of structures will give that equation. That is for simply supported. If it is a continuous beam, you should be able to find out the deflection using softwares. Okay, but the main things here, the deflection value should be based on the values for short term. Say if you have, say the equation will be something like this. Okay, for any different loadings or continuous or incontinuous, the number might be different. If you have uniformly distributed load, it is something like this. So this is the loading case. So for SLS, so deflection normally is something WL to the 4/EI. Okay, so this is the format of the deflection. So the W SLS load for short term this is the load combination. Where that number comes from, where this comes, AS 1170 part 0. Okay, short term and long term factors are given in AS 1170 part 0. There are tables, depend on the purpose of the building, the purpose of the member. You should be able to find out the W values. Okay. So now I need to find out the W, whether it's a short term or long term. So the loads are here. L value, what is L? The span. Yeah, center to center span, you should be able to find it. The E value, the value for concrete, because we changed everything. We changed everything. Yeah, I think someone is joining now. Yeah. So those who are in Melbourne, the class will start from 2 o'clock. Okay, I understand you might confuse, so there's no problem for this week. Just let your friends to know, because the time has been changed in Melbourne. Okay, so now the class will start from 2 and finish by 4. So make sure you adjust your time, so not only in the clock, also in the timetable. Okay, please check that one. I think so timetable automatically show that one if you select the week 5 or week 6. Okay, just ensure you share the information to your friends as well. Okay, so you have short term, long term load, WOK, LOK, E is concrete, because everything we changed to concrete. So what is I value? The I value, they said I is equal to I crack So this is the effective I value. So this is given in the standard. Cannot exceed I effective maximum, that is given. So look at this. So this is the cracked section. This is uncracked. So we need both I's to get the effective I value. Okay. So if we use the softwares to calculate, the the deflection, make sure you have correct I value. Okay, W normally comes from the loading, that's okay, you can put the different load combination, that should be fine. L is there, E of the concrete, okay. I value, it is not same, so it is different, so you need to make sure you use the correct I value. So this is the effective I value. So then you should be able to find out I. To calculate this effective I, so we already calculated I values, we also need MCR, cracking moment. M star is the moment at the section, so you will get it from the bending moment diagram for the given loads. But MCR is the cracking moment, at which stage the cracking will start. In other words, at what strength, what load the cracking will start in the beam. Okay, so it's well before the ultimate limit states, definitely. Okay, so when you apply the load, actually the concrete can take little bit steel, so in the serviceability, we let concrete take the tension a little bit, so initially it will not crack. If you further increase the load, the cracking will start. So that moment is called cracking moment, MCR. So how to find out cracking moment? They gave an equation. They gave an equation. They gave an equation here. Okay, Z is the section modulus of uncracked section. The FCF is the flexural strength of the concrete. You should be able to get it from the section 3.1. You go to the section 3.1, there's a table. You should be able to get the flexural strength. Sigma CS is the shrinkage induced stress. Okay, so that you should be able to calculate. The shrinkage calculation we discussed in the week 1. Okay, the shrinkage is the reduction of length due to chemical action as well as loss of moisture. Okay, so we should be able to calculate the shrinkage. Two components in shrinkage, chemical components and drying shrinkage, moisture component. So you should be able to get that one, the shrinkage strain here. The shrinkage strain here, you should be able to find out. I think we discussed this one in week 1. So if you have any problem, just let me know. That's a long process again. Okay, long process means it's not difficult, but you need to find out one by one. I think I discussed these things in week 1. The first week of concrete design. So you will find out the shrinkage induced stress using this one, and you will find out the cracking moment. The P values are 0 at the moment. It comes with the pre-stress one. So at this stage we don't have any pre-stress, so the P is equal to 0. So this is 0 and this is 0. Both P's are 0. So your equations become much easier. You should be able to find out the deflection. So please work out this crack calculation also. If you know these I values, the crack calculation also is quite straightforward. Okay, I believe we discussed this one. If you still have any issues, please let me know. We'll move on. So there is any questions so far? I think a couple of students may be late. But if you have any questions, please let me know. Okay. Yeah, just again, the class start from 2 o'clock because of the time change. Okay. Before we go into this one, the next part of the tutorials. So I received an email, sorry I couldn't reply that one on Friday. Jeril is here?
Yes, sir.
Okay, so, sorry Jeril, I think you sent an email on Thursday. My apologies, I couldn't reply, but I should be able to explain that one. It should be okay.
Yes, sir.
Yeah, so it's about this the V star calculation. Okay, so if you look at the clause 8232, the maximum shear value should be taken at the face of the column or beam, whatever that support, or at distance dV. Okay, so the reason is there are some conditions for dV. So if you don't have the support width or column width or beam width, you better take at the face of the support, or even if you don't have any of those details, you take at the middle of the support. Okay, those values are higher. So when you have the shear force diagram, generally when you have supports, so if you know that, if you generally the L values comes from here. So in the analysis, the theoretical analysis, shear force diagrams are drawn to the center. So it will go like that. It can be any shape, okay, not necessarily it's a straight line, but let's say it's something like that. So they said you should consider this value or at distance dV or dV, so that value as a V star. Okay, there are some conditions when you can use, but these are the two recommended values. If you don't have any of this, say if you want to get the dV, what is dV? This is maximum of 0.9D or 0.72 capital D. This is dV. Okay, so if you want to get dV, you need to know these values. Okay, and also we need to know, so if you're only given the span but not this ones, you don't have any details of the width of the support, because to get all these ones you need to know L, Ln. Okay? Then only you should be able to get all the values. So in case the details are absent, you should be able to use this value or this value. You don't need to worry about that. Okay, so if you don't have sufficient details, definitely these values are larger than that one. So definitely if you take this one at the support, it's much higher. So maybe a little bit conservative design, over design, but still satisfy all your requirements. Is that clear? Did I answer your question? Yeah.
Yes, sir. Thank you.
Okay. Thank you.
Sir,
Yes.
sir, I have one question, sir.
Yep.
Sir, we need to consider the load combination for designing, sir, to check out the loads like slab, dead loads, and live load for the assignment.
Sorry.
Sir, we need to consider the load combination as well or not? In assignments, sir, for assignments design.
Yeah, for everything we need to consider load combination.
Okay.
Because
Yes, sir. So without considering load combination, we designed the beam, sir, but the movement was so small, so it's.
yeah, sometimes it's first you need to start with the slab design. Okay.
Yeah, we are starting with it, sir.
Okay. So let's start the slab tutorials and
Yeah, sir.
we will discuss today. So when you have design of slab, okay, or when you ask to design a slab, the basic things are covered, most of the basic things are covered in section 8, which is the beam design. Okay, the beam design, especially the rectangular beam design, is very fundamental. So if you have any problems of the tutorial 1 and 2, please make sure you clear all these doubts, and if you have any problem, just let me know. Okay, because those important aspects will come in the slab design as well. So if you have a question or if you have a task to design a beam, we have to start. So the first thing to start the slab design, the slabs can be two types. One is supported by beams or walls, or supported by columns. So this one, we will discuss this one as a flat slab. I will upload that video. That's what I mentioned, that should be available yesterday, but I couldn't make it. There's some issues with the sound, so I need to re-record. It will be available tonight. Okay, so this one is the one we are going to discuss today, and we will discuss this one next class tomorrow. So in your assignment or the project, this is level 1, level 2. Okay, so you need to do the both. So let's look at this one. When you have a slab supported by beams or walls, the support can be two ways. You have the beam on both directions. You have the beams in both direction, or sometimes all four direction, or three. Okay, so here the load, here these are the beams, the plan view. So here the load will transfer on to this both beams, okay, both beams. So technically it will bend like this here in that direction, okay. So the bending will happen like this. Okay. So this will be the span. This will be the span for the slab. So this is called one-way slab. If you have beam in four direction of three directions, the load will transfer to all supports. So here half it's easier, but if you have four, it is question how much it will go here. So we use yield line theory of the failure. So if it is something, because the beam will bend in this direction as well as that direction. Okay, so you have double curvature. So double curvature, the bending about this one as well as this. So double curvature. So we will use a yield line theory. So using yield line theory, we should be able to analyze, and technically that will give the failure lines something like this. Okay. So this is approximately 45 degree at each corners, roughly 45 degree each corner. So that will be the failure lines. So that means all these loads in this area will go here. So these two beams will get a triangle distribution. You can see here a trapezoidal distribution. Okay, so in this one we have two spans. We have two spans. Here only one span. This is the span. So that will be the span of the slab, only one. But here we have two spans. So what we do is we put some names. The shorter span which have the triangle distribution will be named as a LX and LY. Okay. LX and LYs are effective spans in those direction. Effective span. You know what is effective span is? What is effective span? The effective span is equal to so LX and LY, LX and LY are the effective span. So what is effective span? minimum of ln plus d or L. L is the center to center distance from here to there, and ln is the clear span. Okay, so you should find which is smaller, ln plus d or L, so that will be Ly. Similarly, that direction we need to calculate. So Lx and Lys are the effective span. Remember, x and y are shorter and longer spans, not in the coordinate system. Okay, it is not according to the coordinate system. Whichever the span is shorter, that is called Lx. Whichever the effective span is longer, that is called Ly. Okay, that is important, because in the exam, okay, in the class test, some students use Lx and Ly as they like. Okay, so the Lx
What
and
kind of so what kind of question will be asked in the exam, sir? Test?
it will be covered in the whole things from week 1 to week 9, week 12. It will be calculation, like a tutorial questions.
Okay, sir.
Okay, so we'll discuss about the exam question a little bit later. It's week 5 now. Okay, so a long way to go. So you'll try to finish these projects, so make sure you understand each and every steps. If you complete the project by yourself, I think, and tutorials, and that will be okay for the exam. It's not difficult. Okay.
For the design means we need to calculate the loading capacity.
Yeah, design means you need to decide. If you say that design a beam or slab, you need to find out the depth if it is not given, reinforcements, everything, the whole things. But in the exam, it will be clearly asked. Find out the tensile reinforcement or find out the shear reinforcement, something like that. It will not be open like the assignment. The design of a beam or slab means the size of the beam or slab, the necessary reinforcement, tensile reinforcement, shear reinforcement. Okay, that include all the checks: bending check, shear check, deflection check, crack control. Okay, but if in the exam it will be specifically say, okay, find out the tensile reinforcement, or find out shear reinforcement for this shear force. So the exam question will be targeted. The assignment questions are quite open. Is that clear? So don't judge based on the assignment. Assignments are given so that you will work out all possible design things, so that you will understand the whole process. But the exams are targeted because there's a limitation in the time as well. Okay. So Lx and Ly. So what is one-way slab? So this is called two-way slab. So one-way and two-way slabs are named based on the load transfer mechanism. So if the loads are transferred in both directions, it's a two-way slab. If it is in one direction, it's a one-way slab. So when you have something like this, and how to design, that's what we are going to look at. Okay, if it is a one-way or two-way, we will see. But how we are going to design these slabs. So if you want to design the slab, the first step so we need the loads. So if you want to find out loads, we have, as I told, we don't consider the wind load in this assignment, but wind load also will come. Okay, so don't say that the slabs are only subjected to dead load, live load. If it is internal, but the wind load also may come, but we don't cover the wind load in this unit. That's what we don't consider. So we have dead load and live load. We had to find this one, table 3.4 of AS 1170 part 1. So that's generally in kilopascal. Okay, so that is in kilopascal. So the dead load self weight plus any other permanent loads we call as a superimposed what is that what is the superimposed dead load means? Any other permanent load other than the self weight of the slab. It can be tiles. Okay, so if you put tiles on top of the slab, tiles, it's a permanent load sitting always with the slab. That is on the top. The bottom side, it can be any ceilings, can be any services. Okay, so you can have some pipes that need to hang. Okay, that pipe means pipelines or wirings, everything. Okay, air condition if you have ducted one. So there are several different things. It depends on the purpose of the building. The superimposed dead loads may be from 0.3 to 1 kilopascal generally. Okay, if you look at the ceilings and the services, but if you have tiles and other things, it may be a little bit up. You should be able to see what is the self weight of the tiles and others if you want. Okay, so if you don't have, say, something like a project at the moment, you may not have all the details. You may assume we'll take superimposed dead loads of 0.9 kilopascal. That should be fine. Okay, you don't need to calculate each and every step, but I think it's given, some details are given in the standards, sorry, in the question. If it is the tiles and the ceilings are given, you should be able to use that values. If it is not given in assignments or any other places, you should be able to assume some value. Okay, generally those details are available when you have actual design. So that is a superimposed dead load, so you should be okay. Then what is a self weight? So to find out self weight, this is D times raw concrete. Depth of the slab, I put DS, depth of the slab times raw concrete. Raw concrete is a density of concrete. Use 25, not 24. Okay. If you look at that AS 1170, ES 1170, part 1, the density of concrete is given as a 24 kilonewton per cubic meter. 24 kilonewton per cubic meter. But they also said every 1% of steel, the sulfate will increase by 0.6. Okay. So that means if we provide 1% of steel, the sulfate of the reinforced concrete become 24.6. 2% steel make the sulfate as a 25.2. Okay, so at the moment I don't have the steel details because that's what we are going to design, or that's what we are going to determine. So in that case, when you start, okay, you use 25. Okay, 25 kilonewton per cubic meter might be a good value to start the design. Even the later stage should be okay, because 25 kilonewton per cubic meter means it will cover up to 1.6% of steel. Okay, 1.6% of steel. Normally in the beams and slab, our reinforcements are around, in slab it is much lesser, but it will be less than 2% in most of the beams as well. Okay. So for beams and slabs, this will be covered all the possible cases in most of the cases. So 25 kilonewton per cubic meter might be a good number to start. In some cases, in columns, we might put more steel, and that time you can increase later. Okay, please use 25 here if it is not given otherwise. Okay, if the question comes with the value, use that one. That's not a problem. And depth of the slab, we don't know. If you know the depth of the slab, use it, but if you don't know, we need to assume. Okay, so if so if you don't have the DS value, if you don't have that DS value, you need to assume some numbers. Okay, in slabs generally small d will satisfy bending and shear. Okay, about 100 or 125 thickness will satisfy for slab bending and shear checks, but deflection makes a problem. Okay, so deflection will make the problem. So we have to check our assumed D with the deflection. So for deflection check, we use there are two deflection checks. One is simplified method, and other one is team to confirm method. So here we'll use the deemed to confirm method that is given in 9.44. Okay, 9.44. We'll work out the numbers, but first we will see what we need to do. So when you have one-way slab, this is a span. If it is a two-way slab, which span should be used? Which span should be used? We have shorter span and longer span. Which span I should use for two-way slabs? Because the deflection, if it is a two-way slabs, the deflection will happen in both directions. Yeah, the curvature will happen both directions. So, which span will give larger deflection? Shorter span or longer span? So, if you have two-way slabs, it should be shorter span. Okay, the shorter span direction you will have larger load transfer. So the shorter span is the critical for deflection, and also you get larger bending moment along that direction. So shorter span is a critical one. So the deflection check need to be completed for shorter span in two-way slab. In one-way slab, no problem, we have only one span. Okay, so we need to assume and check for the deflection, and if it is not satisfied, you need to increase and make sure. Okay, so once you have the deflection fixed, we need to do the analysis. Cross 6.10, bending moment diagram, shear force diagram. Okay, for one-way slabs, so if you have one-way slab, something like this, so let's say you have beams like this. Okay, this is the span for the one-way slab. Yeah, for one-way slab, this is the span. So we will take 1 meter strip, we will cut 1 meter strip along the span. We'll take a strip, 1 meter strip, okay, we'll take a 1 meter strip, so if you look at this one from here, so you'll see a beam, a slab. This is the slab 1, this is the beam 1, this is beam 2, beam 3, beam 4. Okay, so this slab is supported by 4 beams. So when you look at that one, beam 1, beam 2, beam 4. Okay, So this will be beam 1, beam 2, beam 3, beam 4. This will be the, so actually the 1 meter width. Okay, if you consider, if you take the 1 meter strip, it looks like this. Yeah. Is that okay? Okay. So this looks like the beam design. So in the beam design, this become beam and these are the columns. Remember, the continuous beam supported by columns. Very similar configuration in one-way slab. Only different is the beam width is maybe 200, 300, something like that. This is 1 meter. That's all. Okay. So this one is exactly same configuration except this width. This is exactly same configuration that we studied earlier. A beam is supported by columns. Yep. So this is column 1, column 2, column 3, column 4. This is a bit, can you remember this one? So this is exactly same configuration. So we can use clause number 10, which we discussed under the beam, to draw the bending moment diagram for this. Yeah. So if you remember, we work out FD ln squared upon 16, something like that. Some numbers, if you remember. This is the clause I'm talking about. Simplified method for continuous beam and one-way slab, same clause. Okay, this is what we discussed. And then if you look at the bending moment, I think I put a separate video for the beam. Yep. So you should be able to draw the bending moment diagram using these coefficients for these one-way slabs. Yep. So you have bending moment diagram and possibly shear force diagram also using the same clause. So you should be able to draw the bending moment diagram or find out bending moment diagram at each locations. Yeah. Is that okay? So now the question is, what about this two-way slab? This is for one-way slab. And what will happen for two-way slabs? So if it is a two-way slabs, technically you have several beams. So we have all our, let's say all the lines are beams. So we have 3 by 3, or if you want, 3 by 3, okay? So each one called panels, slab panel. It's a two-way slabs. It is called slab panels. So we have, this is corner panels. Yeah. And these ones there are four. In corner panels you can see we have two sides continuous, here non-continuous, there's nothing here, yeah. So here no beams, sorry, no slabs, so in the corner panels two adjacent sides are continuous, two sides are discontinuous. Okay, all the corner panels are like that. And we have this one, okay, this is edge panel, but the edge panels are not same. This ones are same, this one and this ones are same. Why? Here the longer side is discontinuous. Okay, in edge panels only one side is discontinuous. Only one side is discontinuous. Only one side is discontinuous. But here you can see this is longer side is discontinuous. Here shortest edge is discontinuous. So depend on where we are sitting, we may have two different edge panels. And this one is called interior panel. Where all four sides are continuous. All four edges are continuous. So here also I need to decide the loads. If I want to decide the load, I need the depth of the slab. So if I want to find out the depth of the slab, I need to do the slab deflection. So I know that for the deflection check I need to use the shorter span, so that's fine. But here we have four different panels, corner panels, edge 1, 2 and interior. Four different panels are there. So the shorter span is critical, I know. But in each and every panel we have shorter span. But which panel is more critical? We have four choices: C, E1, E2, I. Which one is more critical, or which one will give larger deflection? What do you think? Which one will give larger deflection? So in this case, which is worst case, the corner panels will give the larger deflections because two sides are discontinuous. So nothing to stop the bending moment, or less resistance the bending at discontinuous edges. Okay. So the corner panels are more critical. Okay. So corner panels are more critical. So what you need to do is you need to consider the corner panel and assume a depth for that, and take the shorter span of that panel, check for the deflection. Okay. If that one is satisfied, all other panels most likely should be okay, unless they have different loadings. Is that clear? Okay. Corner panel is is the more critical one. So, okay, so 1 minute, okay. So that should be okay, we can finish tomorrow. So the corner panels are more critical, so I decide that one. Then I need to find out the bending moment. So again, to find out bending moment, most likely we will use the corner panel, and also better to use some intermediate as well. So use both panels. We'll discuss how to find and why we need in the tomorrow's tutorial. Okay, so I will make the tutorial questions available at the end of the class today after 8 o'clock. I have 7:30 class finish. Okay, so I will put the tutorials and see. You should be able to look at that one. In the video I will put for the flat slab, but I don't think we'll do the flat slab tutorial, but I will